Hey guys, in this video, we're going to learn how to calculate free energy. So first of all, we have to understand what is free energy. Free energy is defined as the energy that's available to do work. So we can harness free energy and do something with it. In this case, when we're talking about electrochemical cells, if we're looking at a galvanic cell, we can harness that energy and transfer it to electrical energy. So we're actually trying to figure out how much energy is being transferred there. Now, when we measure free energy, we measure it in very specific units. These units are called kilojoules per mole reaction. So that's very important to remember the units that are involved in free energy. And we'll talk about why we get kilojoules per mole reaction for our unit. All right, so energy available to do work. We want to calculate delta G, which is free energy. So delta G is the symbol that we give free energy. And it's really important to know what free energy tells us. Not only does it tell us the quantity of energy that's available to do work, but the sign that you get for free energy is important as well. If you have a positive delta G value, what that tells me is that the reaction is thermodynamically unfavorable. Unfavorable. Remember we talked about thermodynamically favorable versus thermodynamically unfavorable when we were discussing the difference between galvanic and electrolytic cells. Electrolytic cells are termed thermodynamically unfavorable, which means the reaction does not happen on its own. I have to do something to force the reaction to happen. Galvanic cells, however, are thermodynamically favorable. And thermodynamically favorable get a negative delta G quantity. So there's lots of questions that are super easy to get points on. They might say, calculate the delta G and determine if the reaction is thermodynamically favorable or not. Or they might use the older term spontaneous or not. Remember, spontaneous and thermodynamically favorable mean the same thing. Thermodynamically unfavorable and non-spontaneous mean the same thing. So when you see those older questions, you'll see the words spontaneous and non-spontaneous instead. When we, on today's exam, when we need to discuss that, we want to use these terms, thermodynamically favorable or thermodynamically unfavorable. And remember, that means that the reaction happens on its own or not. Negative delta G's are thermodynamically favorable. Positive delta G's are thermodynamically unfavorable. So going back to the questions that AP like to ask is they'll have you quantify or calculate the delta G quantity of energy, and they'll also have you look at that quantity and determine if the reaction is thermodynamically favorable or not. And you can determine that just by looking at the sign of the delta G that you end up getting there. All right, so now we've talked about the sign, what free energy is, how do we determine that. Let's talk about how we figure out or quantify the amount of free energy that we have. So we use this equation. Notice how you have this little naught symbol right there? Remember that means at standard conditions, which is 1 atmosphere, 1 molar for my concentration, and 298 for my temperature there. So I want to pick apart and understand what each individual thing in this equation is. First of all, delta G is equal to negative NFE. And you'll hear me say it negative NFE, just to say it pretty quickly. This equation is on your equation sheet. So let's talk about what N means. N right here stands for moles of electrons transferred. moles of electrons transferred. Now remember at the very beginning when we did redox and single displacement, and I kept asking you guys, how many moles are transferred? How many moles are transferred? And that we would have to plug it in somewhere in order to get it correct. This is where we plug that in. So N stands for moles of electrons transferred. It's very important that you get this N number correct because a lot of the times the AP readers will give you 1 point just for getting N correct. And it's a very easy point as long as you know how to do it. This next symbol here, F, this stands for Faraday's constant. Faraday's constant. Because it is a constant, it is going to be the same number every single time. If you look at it on your equation sheet, it's actually 96,485, but we're going to use 96,500. So it is a constant, that number does not change. Now it's also important to know what that means. So what are the units involved here? So that's saying that 96,500 coulombs is equal to 1 mole of electron. Coulombs is a unit that we give things that are charged. Because we have electrons that are moving in a wire in electrochemistry, we get a charge. And so that is where the coulombs is coming from. Now, this hopefully looks familiar to you. This is a little E with the not symbol, and so this stands for cell potential at standard conditions. So the way we find our cell potential from standard conditions, remember that is where we take our E cell of our reduced species minus the E cell of our oxidized species, and that gives us this E cell, okay? So I want to talk about how do we get kilojoules per mole reaction when we calculate delta G. We have to plug in all of the units for each individual thing. So let's start with the N. Remember, N is measured in moles of electrons. So if I want to say delta G is equal to moles of electrons, that's what N stands for. F stands for Faraday's constant, which is in coulombs per mole of electron. So I'm going to put in coulombs per mole of electron. And then we're going to plug in E cell's units. Now remember that E cell is measured in volts. Well, a volt is equal to a joule per coulomb. So it's the amount of work per charge. That's what cell potential is. Work is usually measured in joules. Charge, remember we just talked about, is measured in coulombs. So if I plug in my volts here, I get joules per coulomb. Now let's simplify our units here. So you see how moles of electrons is on top and bottom. They actually cancel out. Coulombs is on top and bottom, so they cancel out as well. So the unit that we're left with here is joules. But wait a minute, Gullich, you told me that this is measured in kilojoules per mole reaction. Why are we just getting joules right here? Well, what we have to do is convert these joules to kilojoules first of all. Now, how do we convert joules to kilojoules? What we do is we divide by 1,000. So once you calculate, you plug in your N value, your F value, your E cell value, and you calculate your delta G quantity, you will then have to convert that to kilojoules. And the way you do that is by dividing by 1,000. So 1 kilojoule is equal to 1,000 joules. So that is a conversion factor that you need to know in order to be able to convert between joules and kilojoules, what we need our unit to be in. And this will all make sense when we do an example problem. Well, now I still haven't answered the total question. I know kind of where this is coming from, but where is this per mole of reaction coming from? This is put onto the end of the unit after we've converted to kilojoules, because that is telling us how much energy we get for just one thing of the reaction happening. So if we have double the reaction or triple the reaction, we would get double or triple the amount of delta G energy that we have. And so this is specifying that this is the amount of energy we get for one go round of the reaction. And it's very important that you include that. So now that we know what free energy is, what free energy tells us, how to calculate free energy, let's do an example problem together. So in this example problem, I have copper 2 plus iron yields copper plus iron 2 plus. And I want to do a couple of things here. I want to calculate delta G, but I also want to figure out what that tells me. So what information is that telling me? Is the reaction thermodynamically favorable or is it unfavorable? So I have to know a couple of things here. First of all, I have to have a balanced reaction. And I look here and I notice that my charges on both sides are balanced, so I have a balanced reaction. And just to get some more practice, I want us to be able to write those half reactions. So for copper 2 plus, going to copper, I have this as my foundation for the half reaction, and I need to include 2 electrons, and the side that I include them on will tell me what is actually happening here. So I have to balance my, my charges here. So I have 2 electrons, and that's going to go on this side in order to balance out my charges to make it equal. Now, what is happening to the copper? Is the copper reduced or is the copper oxidized? Your answer is the copper is reduced because it's going from a 2 plus to a 0 charge. Now, we also have to do something else with this. We have to look up on our standard reduction potential chart what that value is for the copper 2 plus going to the copper solid. And if you look at the chart, remember that I posted it online for you guys. It's in this big old note packet. If we look that up, we get 0.34 volts for my standard reduction potential. Now this is important to know because we're going to have to calculate our cell potential in a little bit. Well, now let's look at the other end of the spectrum. So iron going to iron 2 plus. And so we're going to write that half reaction, write the foundation for it here. I see that there's a 2 plus on this side and a 0 on this side. So we have 2 electrons transferred. And I'm going to put those electrons on this side to be able to balance my charges and cancel them out. Now, I would find this equation on your equation sheet, but remember that they always want the reduced. All of these equations are reduced on this sheet. And so if you have something that is oxidized, which is the case for this, it will actually be backwards on your reduction potential chart because that's only showing reduced half reactions, no oxidized. And so when I look up that value there, my oxidized iron 2 plus and iron solid gives me a negative 0.44 volts. Now remember that the more positive value of the two is always reduced, and we got that correct because this is a more positive value than this. So now that we've done some foundational kind of review things, we can go into calculating delta G. So when you're calculating delta G, I want you to plug in not only the numbers, but the units as well, because that's going to help you remember, especially when we're learning a whole lot of other things. It's going to help you remember to cancel out my units and not to forget to convert at the very end. So let's get that going. I want to use green. So we're going to plug in delta G equals negative n phi. We have those little not symbols, which means that I am at standard conditions. So let's plug in N first, okay? Now remember, N stands for moles of electrons transferred. Where I get that number is I look at my half reactions, and that's why I wrote this down here. I look at this half reaction and this half reaction, and I ask myself, what is the common multiple, the least common multiple between the two? That will tell me how many total electrons are being transferred from the oxidized species to the reduced species. So I look here and I see a 2, and I look here and I see a 2. That tells me that 2 is the least common multiple that I have here. So that is going to be my N value. Now remember, they'll give you 1 point for just getting N correct. So I'm going to plug in 2 moles of electrons here. Now, the next thing that I plug in is my F, which is Faraday's constant. And remember, that number is always 96,500. It is on your equation sheet if you forget it. So I'm going to plug in 96,500, plug in your units, coulombs for every mole of electron. And now for the very last thing that I'm going to plug in is my standard E cell value. So I'm going to find that up here. I'm going to do some scratch work. Remember that standard E cell is equal to the E cell of the reduced minus the E cell of my oxidized species. So we said reduced is the 0.34. E cell at standard. And the oxidized is 0.44, negative 0.44, so it's reduced minus oxidized. And so for that value, we get 0.78 volts, okay? Now remember what volts is equal to. 0.78 volts is like saying 0.78 joules per coulomb. So I'm gonna plug that value in right here. 0.78 joules per coulomb. Now, I'm at the point where I can work my math. So, I see my units that I can cross out. Moles of electrons cancel out. Coulombs cancel out. And I'm left with just joules. So, I'm going to go through and work this math. Don't forget that that's a negative sign right there. So, I'm going to take negative 2 times 96,500 times 0.78. And I've calculated it on my page here. So let me see if I can find it. When you do your calculation, you get this for your answer. Delta G at standard conditions is equal to negative 1.5 times 10 to the 5th joules. Now we're not finished there. This is not our final answer. Remember, our final answer, we don't want joules. We want it to be in kilojoules per mole reaction. So what we have to do is take this quantity and divide by 1,000. And that will give us our final answer that we can put our proper units on. So delta G, I'm transferring my markers because my black wasn't working that well. If I take this number and divide by 1,000, that's equal to negative 150 kilojoules, I don't want to just leave it in kilojoules. I want to say that's how many kilojoules I get for one reaction. So that's what this is telling me, how many kilojoules for one reaction. And that is my final answer. That is delta G. Now, let's kind of evaluate this. What is this telling us? Well, this is telling us that we're getting 150 kilojoules per mole of reaction of energy available to do work. And more importantly, because this quantity is negative, that is telling me that this reaction here is thermodynamically favorable. The reaction happens on its own. And another piece of important information, because this quantity is negative and our E cell value is positive, that tells us that what we're working with here is a galvanic cell. All galvanic cells will have positive E cell values and negative delta G values. That is an important sign convention thing that you need to know. They like to ask some multiple choice questions dealing with that. So I hope this was helpful. I hope that you guys are able to do delta G now. Let me pause it, sorry.